gloss over those as they go by. And in 235, you should be able to pick those up easily. Alcohols. Basically, we're dealing with the functional group OH. Ethanol, the classic alcohol of consumption. This is cholesterol. Here's the OH group. Beta-D-glucose. The beta refers to the stereochemistry at this particular carbon. And again, it's a polyalcohol. Other notable alcohols, this is isopropyl alcohol. More properly, it is 2-propanol. We'll do nomenclature in just a moment. Terbutyl alcohol. We used a very similar alcohol in lab here. 2-methyl-2-propanol. This is glycerol, a triol. This is an allylic carbon, if you recall from chapter 10, I believe, and this is typically referred to as allyl alcohol. It is more properly 2-propene, 1-ol, and this, of course, is benzyl alcohol. These are common alcohols, and again, they're typically referred to by their common names. For nomenclature, you want to pick your parent chain such that it contains the hydroxyl group. We'll take the root and we'll replace the E with OL. We'll get a number in order to give the hydroxyl group the lowest possible number. And of course, we're going to do substituents alphabetically. Pretty much a standard set of rules. Just remember the alcohol is a high priority, and therefore it will take charge in terms of the numbering and the parent chain. If we were dealing with this guy, our parent chain must contain the OH group, so we're going to go down here. We're going to number it so the alcohol gets the lowest possible number. This is going to be a 2-ol, and we have methyl groups here at 4 and 5. We would call this 4,5-dimethyl, 2-hex-and-ol. Now there's another nomenclature that is often used, and that is to move the 2 from here down to in between the N and the OL. We'll see some examples of that in just a moment. Once again, we have a parent chain that's going to look like this. We're going to have a bromine here in carbon 1, alcohol in carbon 2, and a methyl group. We would name this guy 1-bromo, 2-methyl, 2-butanol, or we can move the 2, like I said, from here before the but and stick it down here before the ol. If you have a complicated multifunctional molecule, this is very, very common. This is fully acceptable. Either one, follow the IUPAC rules. Let's just go ahead and do some very quick nomenclature. For our first one here, instead of RNS, go ahead and use cis strands. Remember that a benzene ring is referred to as a phenyl substituent. Again, we haven't quite covered that yet. This is going to be a diol. It's a cyclohexane diol. These are both equatorial, and they are 1,3, so that makes them cis. So we could simply name this cis-1,3-cyclohexane diol. With this guy, we have a parent chain down through here. It'll let this be carbon 1. Going to have a phenyl group, and we're going to have a methyl. We could call this 4-methyl-1-pentanol. Once again, the parent chain, 4-carbon chain or 5-carbon chain, 1, 2, 3, 4, 5, is defined by the presence of the alcohol, and we simply have a phenyl group as a substituent in carbon number 4. Here we have a cyclohexane with a couple methyl groups on it. In the past, we would look at this and say, well, immediately we want that to be carbon 1. Remember, we want the alcohol to have the lowest possible number. So we're going to make that carbon 1, simply call it a cyclohexane-ol. And we're going to put our methyl groups here at carbon 4. Because this is, by definition, going to be carbon 1, we don't have to include it in the name here. Any questions on these? Let's just do a couple more in reverse. The first one here is a pent, so we have a 5-carbon main chain. Going to be hydroxyl group in carbon 1. And out here we're going to have methyl groups on carbons 3 and 4. Fairly simple molecule. Should look like that. This is a diol. It's a cyclopentane diol. We have cis stereochemistry. And we have alcohol groups in carbons 1 and 2. You could draw the ring itself in the usual way, or you could use wedges as I've done here, as long as you indicate the cis stereochemistry. This is an ethanol, so we have 2 carbons in our parent chain, and at the end, so our terminal carbon, we have a phenyl group. There's our 2-carbon parent chain, and here in carbon 2, we have our phenyl group. You'll note that benzene rings are going to be drawn a couple ways. One is this way as cyclohexatriene. You will learn that cyclohexatriene is a very nice way to represent benzene, but it doesn't really describe it very well. The other way, you simply use a circle in the middle here to indicate that we have delocalized electrons throughout the ring. Cyclohexane diol, cis-1,3. So we have our cyclohexane ring. We're going to have hydroxyl groups on carbons 1 and 3. Once again, to make them cis, they would both be equatorial, or you could simply use wedge bonds like that. For phenyl-1-pentanol, again we have a 5-carbon chain. In carbon 4 we have a phenyl group. So there's our 5-carbon chain. There's our hydroxyl group. And we'll stick our phenyl in carbon 4. And the last one here, cyclohexane-ol, cyclohexanol. with 4,4-dimethyls. You've seen this one before. It simply looks like this. Any questions? Bonding in alcohols. The oxygen, of course, is going to be sp3 hybrid or something very close to it. So this is our oxygen atom here. These are our lobes of electrons. Remember, most of the reactivity of the alcohol functional group is going to depend on these things. This forms a general tetrahedral structure. Bond angle is about 109 instead of 109.5, but that's close enough. Electrostatic potential map. Not too surprisingly, this is a nice polar covalent bond here. The oxygen will draw the electrons towards itself. This is where our two lobes of electrons live. And again, virtually all of the chemical properties here are going to depend upon this electron pair. We know that we have hydrogen bonding. Alcohols do it fairly well, of course not as well as water does. We can form, for every oxygen, we can actually form 2 hydrogen bonds. But we only have one hydrogen here to participate. Not nearly as effective as water, but certainly fairly good. Ionization, we talked about this way back in chapter 2 or something like that. This is our first functional group that really undergoes significant ionization. Remember, we represent this by a dissociation constant, Ka, and it simply is products over reactants looking something like this. Water is a liquid, and according to the rules, that is left out of the expression. For most alcohols, this equilibrium lies fairly far this way, with pKa's above 14. For ethanol, it's actually 16. So our pKa here would be 16 for ethanol. Again, very far to this side of the expression. We can do substituents on our alcohol. This is ethanol where we just were. Water's down, almost the same thing. As we put electron withdrawing groups here, we can actually make this fairly acidic. This is acetic acid and trifluoroacetic acid, just for comparison. If we put 3 trifluoro groups here on a tert butanol, we can drop it almost as much as acetic acid. Again, it follows a fairly simple thing. Remember, when you're doing something like this, you're simply stabilizing the anion, and that shifts the equilibrium this way, so we get a lower pKa. If you look at trifluoroethanol versus ethanol, again, we have a shift of almost 10 to the 4th in acidity just from the fluorines here. Again, these are highly polarized covalent bonds. They basically move the electrons from the oxyanion down here. Can't do that this way, and that's worth our 10 to the 4th in terms of dissociation constant. If we look at this in terms of electrostatic potential, again, we can see we really take the oxyanion away, move it out here to the fluorines. Here we have lots of anionic character. Not too surprising. Any questions? Phenols. You will meet phenol, I think it's in chapter 14 when you do aromaticity. Again, this is an OH group that's attached directly to a benzene ring. Benzene ring tends to acidify the OH group significantly. Our oxyanion here, this is our dissociation constant once again. Phenol is called carbolic acid, if you remember. Carbolic acid and phenol was one of the very first antibiotics, and it was actually used in surgery. Now, it will choke you and or kill you. So, it was, but it worked. It worked. It was a nice antibiotic, sort of.
Worked too well.
Right. What they used to do was have an aspirator that would be blowing this phenol solution all over the patient and the surgeon. And what you would have to do is take a deep breath, run in, cut like mad, run out, take another breath. Hopefully the patient's head was sticking out the other end. So.
Anesthetic.
Not, it was antibiotic. Yeah. In fact, for many, many years, antibiotics were rated by their phenol number. That was how much more effective they were than phenol. Now they're, 10,000 times or something. But first day, it was really pretty good. For phenol, pKa of about 10. If you put substituents on the benzene ring and you don't know what those are, you can drop this down, but you can deal with that in chapter 14. We can make alcohols commercially. We make tons and tons and tons, billions of gallons. Typically, commercially, they use something called synthesis gas. You heat coke. This is the same coke that they use in production of iron. And you heat it up with steam, and you produce synthesis gas as one of the products. In the presence of a catalyst at very high temperature, you can form methanol. Again, huge, huge concentrations. Hydration of ethene is a very nice way to make ethanol. Turns out that there are natural gas wells that spew out ethene. And all you have to do is hydrate this in the presence of a catalyst, and you make ethanol. Apparently there was a factory that was built to do this down in Texas. And the government insisted that the entire factory be built on stilts so that inspectors could walk underneath it to make sure that nobody was siphoning off the ethanol. Ethanol is actually very, very cheap. And, this is pure ethanol. But it turns out that people were siphoning it off anyway. Doesn't matter. Because the pKa's of alcohols are fairly high, if we want to use an alcohol as a nucleophile, quite often you will convert it to the oxyanion, the alkoxide. Simple way to do this is simply dissolve something like sodium or lithium in the alcohol. Again, it undergoes the fizzing reaction, releasing hydrogen and forming the sodium alkoxide. Sodium amide's another nice way. Again, we've seen this. It's a very strong base. Here we form the sodium alkoxide. And we'll talk about, maybe we talked about this in chapter 11. Alkyl lithiums, again, this behaves as if it's a carbon anion, pulling off the hydrogen to make the lithium alkoxide and bubbling out methane. The alkoxides are very nice nucleophiles for SN2 reactions or for promoting elimination reactions. Now we already know lots of ways to make alcohols. This goes back to our chapter on alkenes. So let's just look at these. Simple hydration. We remember that simple hydration has a carbocation intermediate. Because of that, we can have rearrangement. And of course, we have Markovnikov regiochemistry. If we do a more civilized hydration with a mercury 2 acetate, followed by more hydride reduction, we can form the alcohol without rearrangement and still keep the Markovnikov regiochemistry. Hydroboration oxidation. This gives us cis addition for the hydroxyl group and hydrogen, and again, anti-Markovnikov regiochemistry. And making diols, we know that we can use permanganate, alkaline permanganate with an alkene, and we form a cis 1,2 diol. Those are things that we know. We can also make these by, we'll see this in this chapter, by reduction of aldehydes and ketones. We will use borohydride or lithium aluminum hydride. Lithium aluminum hydride is a very powerful reagent. If we have an aldehyde and we use sodium borohydride or lithal in ether, we will form a primary alcohol. What we're basically doing here is adding H- to our carbonyl carbon. Oops. If we do this with a ketone, we form a secondary alcohol. Once again, we'll talk more about these, but these reagents simply add H- to the carbonyl carbon. We saw Grignard reagents back in chapter 10, I believe, or 12, or 11, something. Here we have a carbon anion in our R group. We can simply add this to a carbonyl, and in doing this, we form a secondary alcohol from an aldehyde. If we have a ketone, we get a tertiary alcohol. We'll talk a lot about the Grignard reaction in just a bit. The mechanism of a simple lithal reduction. This is a representation of lithium aluminum hydride. Here's our aluminum, and we have 4 hydrogens attached. Basically, what we're going to do is to just donate H- directly to the electrophilic carbon here. There's our H-. As it forms a bond here, in order to keep carbon with a valence of 4, these electrons have to be promoted to the oxygen, and we wind up with the lithium alkoxide. As always, we will take this, dump it in water, and convert it to the simple alcohol. Lithium aluminum hydride is a very, very powerful reducing agent. This is a reduction as opposed to an oxidation. A very powerful reducing agent. And there's a myriad of reactions that you will learn in 235. Ones that we just talked about here, we'll do today. With aldehydes to get primary alcohols, ketones to get secondary. Esters also react nicely to give us alcohols out here. Reactions with azides, carboxylic acids, these guys are things that you'll cover next semester. Now, I said that lithal was a very effective reagent, and it is. If we take this particular carbonyl compound, we have a double bond and we have a carbonyl. We have nice selectivity. The hydride will reduce the carbonyl in about 94% yield. And really, we don't get very much on our double bond. Sodium borohydride, however, is not nearly as selective, and we'll get, maybe a 60-40 mixture of the desired product, and this one where we have over-reduction and we lose our double bond. In spite of that, if you are in a lab, especially our labs here, and we did a reduction, we would always use borohydride instead of lithium. The reason is that lithium aluminum hydride is extremely flammable. It just whooshes in air like mad. And you have to do this in an ether solvent. And if you recall, ether is very explosive. So we have a low boiling, explosive, high vapor pressure solvent, and something that as soon as you get it wet with moist air will burst into flames. Kind of a neat little thing. Lithiol is much more selective, doesn't reduce the alkene. Here we have a little bit of lithiol, and somebody just dropped in a drop of water. So it's definitely not something that you want to mess with. Fairly dangerous. Very nicely selective, but fairly dangerous. All right, let's go ahead and just work backwards here. Here we have a bunch of alcohols that we have made from lithium aluminum hydride and ether. Simply give me the appropriate carbonyl compounds that would give these products. You have to remember that all you're really doing here is you're adding an H- to a carbonyl carbon. That means that wherever you see the hydroxyl group, that's where the H- went. And this used to be a carbonyl carbon. So all we do is convert this to our double bond, and that's our structure. Once again, the hydride from lithium aluminum hydride went to this carbon, so that means this was a carbonyl, and it was simply this ketone. Oops. For this guy, once again, this is the hydride that we just added, which means that this was a carbonyl, and this was this substituted cyclohexanone. Hydride is small. We do have a methyl group here, so that will offer some steric hindrance, but of course we will get both isomers at this carbon. Any questions? All right, back in chapter 11, we talked about the basics of Grignard reagents. Grignard reagent is a very powerful thing, and it's very useful for making alcohols. Essentially, what you're going to take is an alkyl halide, magnesium metal, and we're going to do this in diethyl ether. When you mix these things together, we form this compound. This is cyclohexyl magnesium chloride in this case. The reaction is really quite good. conversion of the alkyl halide to the Grignard is about 96% effective. Nice thing about a Grignard is we can make it with simple alkyl halides, primary, secondary, doesn't matter. We can also do it with aryl halides or just simple vinyl halides. Again, the same reaction, magnesium plus bromobenzene in this case, give us the phenyl magnesium bromide. These things must be done in ether, as we said back in chapter 11, and that's because the ether actually complexes with the magnesium. This is methyl magnesium bromide without the ether. Here we have it with the ether. This is our methyl magnesium bromide. Here's the two ethyl ethers stuck on there. And again, if you look at the electrostatic potential maps, we have much more carbanion character on the methyl group once we do our chelation than we do in the simple version. This is the ether, again, is an essential part of the reaction. The mechanism is very simple, really. We're going to take a generic alkyl magnesium halide and a carbonyl. This has a negative character, and it will simply add as a nucleophile to a carbonyl to give us the magnesium oxyanion. Just like we think of lithium aluminum hydride as H-, always think of a Grignard reagent as simply a stabilized carbanion. Makes it a very, very nice way to make oxyanions. Grignards are very, very powerful. If we were to react a Grignard with formaldehyde, we would get a primary alcohol. If we do this with an aldehyde, we get a secondary alcohol. Ketones, of course, give us tertiary, and we'll see that esters can react to also give tertiary alcohols. So these are the four that we're going to be covering in this chapter. Go ahead and do the products of this very simple Grignard reaction. Remember, simply think of this as a cyclohexyl carbanion. The cyclohexyl carbanion will attack the carbonyl carbon. When it does, it simply forms the oxyanion. Second step in the reaction is always to take this and dump it into mild acid. When we do that, we protonate this to make the corresponding primary alcohol. Once again, formaldehyde plus a Grignard gives a primary alcohol. Go ahead and do this one as well. Here we have an aldehyde. Keeping track of the carbons here, we have a 1, 2, 3 carbon chain. This carbon is our stabilized carbanion. It will simply attack the carbonyl, and that will be our oxyanion. Again, our second step, dump it into aqueous acid and we get the alcohol. Aldehyde, secondary alcohol. Finally, let's look at a ketone here. Our nucleophile is going to be the methyl group for methyl magnesium bromide. It will simply attack the carbonyl carbon. There's our oxyanion. When we dump this into aqueous acid, we have now formed a tertiary alcohol. So formaldehyde, primary, aldehydes, secondary, ketones, tertiary. Any questions? All right, let's just do a couple more. Go ahead and just give me the products. Our methyl group is our nucleophile. Here's our electrophilic carbon. Going to form this as our oxyanion. And we have made our tertiary alcohol. This guy is called benzaldehyde. Oh, go back? Sure, sorry. By now you should be able to write fast. You know, it's our last chapter. As I was saying, this is benzaldehyde. Benzaldehyde has the aroma of cherries. You have artificial cherry flavoring, etc. You're dealing with a little bit of benzaldehyde. Again, methyl magnesium bromide is our methyl group is our nucleophile. There's the electrophilic carbon. There's our oxyanion. And we have made the secondary alcohol. Phenyl magnesium bromide, the phenyl anion is your nucleophile. We are simply going to add the benzene ring itself to our carbonyl carbon. Because it's a ketone, we expect to get a tertiary alcohol. There's our oxyanion, and there is our tertiary alcohol. Grignard reactions are a real staple in organic chemistry. They're reliable, not real difficult to do. Do have to be a little bit careful that you don't, explode things and whatever. But because again, you are using ether solvents, so you do have to be a little experienced in lab in order to do these. But they're very, very reliable reactions. Go ahead and just complete this set. Now here, instead of showing the Grignard reagent itself, this is a common way to show this reaction. We simply are starting with an alkyl halide, magnesium and ether, that's our first step. We understand that that makes our Grignard reagent. Grignard reagent then attacks, and our second step is the acidic workup. In our first reaction here, our nucleophile is going to be the methyl anion. This is our alcohol product, and I've colored them just so that you can easily see. Methyl group from the Grignard added to the aldehyde carbon. In our next one, we're going to make phenyl magnesium bromide. That's going to be our nucleophile. It's going to add to the carbonyl carbon. Because we have a ketone, we made a tertiary alcohol. Our last one here, we have 2-bromopropane. So we're going to make an anion at our carbon number 2 here of our chain. That's going to attack the carbonyl. That's magnesium and ether. Our product would look something like this. Now, we actually will get both stereoisomers at this carbon, but this one is probably the most favored. Here we have a fairly large group, and we're going to play dodgeball with the methyl. So it's going to want to come in on the bottom instead of the top where the methyl is. So this will be the major isomer. This is called acetaldehyde. It is the aroma of green apples, actually. This is our electrophilic carbon. We're going to add the methyl group to this carbon, and we'll simply make 2-propanol. Once again, acetaldehyde with phenyl magnesium bromide. Phenyl group is our nucleophile, attacking the carbonyl carbon. We make the secondary alcohol. And finally, if we take acetone and cyclohexyl bromide, magnesium and ether, our cyclohexyl anion is our nucleophile, attacking the carbonyl carbon to give us our tertiary alcohol. Any questions? Grignard reactions are just like lithyl reductions, are fairly simple because really all you need to appreciate is that we're going to add the anionic species to the carbonyl carbon and then propane it. Now there is one really neat thing about Grignard reactions in synthesis, and that is there's almost always, essentially always, 2 ways to do a Grignard synthesis. Let's look at that. What if I gave you this and asked you to do a synthesis? So I ask you to provide a Grignard reagent and a carbonyl compound. Well, what you would do is you would look at your molecule And you would say, okay, here's the OH group. Now that used to be a carbonyl, right? And one of these things that's attached on either side was a Grignard. So let's just take and let's split the molecule on one side or the other. Let's say that this is the bond we made in our Grignard reaction. Now, if that was the bond, then this was our carbonyl compound over here, and our Grignard reagent was simply this phenyl group, phenyl magnesium bromide. So this aldehyde, everything here, plus phenyl magnesium bromide, add the phenyl group here, and this is our product. If we now split on the other side, we can get our other possible way to do this. Here with the little blue split, the Grignard reagent is this fragment over here, and this side was our carbonyl compound. Putting them together, benzaldehyde, and 1, 2, 3, 4. This is a 2-bromobutane. So isn't that kind of neat? On your exam, I can guarantee you that you will have a synthesis problem very much like this, where you'll be given something and asked to provide 2 pathways to make it by Grignard.
The exam's Thursday, right?
Nope.
No?
Nope.
Tuesday?
It's someday.
Oh.
Sometime. It's coming up one of these days. Remember, we had to, the way the syllabus was written, we had the exam, and then we had chapter 17. And I decided that was stupid. So we're doing 17, then the exam. So. All right, so go ahead and practice. Give me 2 ways to make this guy. I'm going to split on this side first if you want to work there. So let's start by splitting on this side. That means that our Grignard reagent was this 2-carbon chunk, and that our carbonyl had 1, 2, 3, 4, and this was an aldehyde. Let's split on this side. That means that our Grignard was now a 1, 2, 3 carbon chunk. And this 3-carbon aldehyde was the carbonyl compound. questions? Very, very simple. All you have to do, split on either side, identify the fragment that was the Grignard, other side is our carbonyl. All right. Remember, I also said that Grignards reacted with esters to give tertiary alcohols. Now, you need 2 moles of Grignard to do this. The ester synthesis is a little confusing. So you have to think about it. If we take this particular carboxylate ester and react it with 2 moles of Grignard, we will make this tertiary alcohol. Now, clearly, 2 of the methyl groups here wind up as methyl groups in our alcohol. The alcohol portion here, the alkoxy portion of our ester, is totally lost. So it doesn't matter what is attached here at all, as long as it's an ester. This methyl group, however, survives. Let's go ahead and look at the full mechanism. Here's our carboxylate ester. First thing we're going to do is take our generic Grignard. The carb anion is going to add to the carbonyl, and we're going to form this addition intermediate. Now, the reason that this reaction continues to go on to give us a tertiary alcohol is that the alkoxy group here is what's called a good leaving group. That is, we've added a carbanion here. We've made the alkoxy, but because this is an alkoxy by itself, this anion can collapse, kick out the alkoxy group as RO minus, and what have we just made? Well, we made a ketone. Ketones, we already know, react with Grignards. So, we have more Grignard in the pot. We just made a ketone. The anion will now attack. We have our tertiary alkoxide, which we simply protonate to give the tertiary alcohol. The thing to remember, the alkoxy portion is lost, totally lost. It's gone. We have 2 moles of our Grignard, 1, 2, that wind up in our alcohol. And whatever is on this side of our ester carbonyl also survives. Now we'll see some examples of this when we do some synthesis reactions. And this can be a little bit tricky, but just remember the basics. The alkoxy is lost, and this survives. All right, as good as the Grignard is, it does have limitations. Remember, we're dealing with a carbanion, essentially. That means if we have anything, like any of these guys, that have an acidic hydrogen, they're going to protonate the carbanion, here methyl magnesium bromide. The anion will simply pick up a proton and form methane. So we can't do a Grignard reaction if you have any of these functional groups in your molecule. If you also, or if you have things like nitriles, nitro groups, thioesters, stuff like that, Grignards will also add to those. When you do reactions, I think chapter 24, reactions of amines, you'll see that these can actually be useful. But again, if we have this in a carbonyl compound, you can't do a Grignard because it will add to both. So you have to be a little bit careful when you design a Grignard synthesis. Make sure there's nothing acidic, and make sure you don't have other functionalities that can also react. All right, let's go ahead and do a very simple synthesis problem. This is the kind of thing that you might see on an exam, where you're given a selection of starting materials, and you are simply asked to make a compound. Okay? Now, we look at this, and we say to ourselves, it's an alcohol, right? We know that we can make alcohols from carbonyl compounds by simple Grignard reactions. We can also make it by a hydride reduction of a carbonyl. So we want to look up here and see if we can find pieces that we could use to make this. If I look, I have two carbonyl compounds here that are decent candidates. I'm looking for a 3-carbon chain here. Both of these are carboxylate esters. If we took this compound up here and we added Grignard reagent to it, what would we wind up with? What type of an alcohol? A tertiary alcohol, right? Grignard reaction on an ester gives a tertiary alcohol. Our target molecule here is a secondary alcohol. So what you have to do is to realize that because this gives a tertiary alcohol, this is also a carboxylate ester, but the group that's on this side of the carbonyl is a hydrogen. We have hydrogen here, and we have two pieces that could have come from a Grignard. So, just like before, if this was our carbonyl, these are the pieces that came from the Grignard. The piece that came from the ester is this guy in the middle. This is the hydrogen. It survives. The alkoxy is lost. So we need two of the 3-carbon Grignards and our formate ester. Any questions? This is the one exception in an ester synthesis where we can make a secondary alcohol from a Grignard. And again, that's because the hydrogen survives, there it is, and we add 2 moles of our Grignard. All right, back in chapter 11, we also met a reagent called an alkyl lithium. Again, just like a Grignard, an alkyl lithium is essentially a stabilized carbanion. Very polar bond here, lots and lots of negative character on our carbon. Remember, alkyl lithiums can be primary, secondary, tertiary. alkyl, aryl, vinyl, whatever. Just like a Grignard, they're very, very versatile. If we take a carbonyl compound and an alkyl lithium, or aryl lithium, or vinyl lithium, whatever, just like a Grignard, the carbanion is going to be a nucleophile. We're going to add to form the alkoxide. When we take and we dump this into water, we protonate that and make our alcohol. Principle is exactly the same as a Grignard. If we have an aldehyde, we will get a secondary alcohol. Ketone, we get tertiary. Go ahead and look at this and draw the products for this simple reaction. This is a vinyl lithium. So remember, we can make this directly attached to our double bond. We all know what's going to happen. We know that this carbanion is going to add to that carbonyl. It's an aldehyde, so we will get a secondary alcohol. And our double bond is going to go along for the ride. That's our mechanism. This carbon is our nucleophile. The tricky thing here is remembering to put the bond in. Our product looks like this. Once again, this is the bond that we made. This is our carbanion right here. Make this bond and make our secondary alcohol. Only tricky thing about this particular problem is drawing it, because people, for some reason, have difficulty with this bond. But it's a very, very simple reaction, very, very similar to our Grignard. Any questions? Well, let's mix it up a little bit and go ahead and just give me products for these reactions. Our first one, we have methyl lithium. We have an aldehyde. The methyl group will simply add to the carbonyl carbon. This will become a secondary alcohol, and it is 2-propanol. Our next one is a simple classic Grignard. We have phenyl magnesium bromide. We have an aldehyde. We will form a secondary alcohol. The phenyl anion will add to the carbonyl. This will become an OH. And we will get that alcohol. This is the other way to show the Grignard reaction with the alkyl halide, magnesium and ether followed by acid. The cyclohexyl anion will simply add to formaldehyde. Now, because it's formaldehyde, we're going to make a primary alcohol. And it will look like that. Any questions on this set? Then let's do another one. All right, this is an ester, isn't it? What do we remember about an ester? The group on one side of the carbonyl, this side of the carbonyl, is going to survive. The alkoxy portion is lost, washed down the drain. We are going to add 2 moles of methyl magnesium bromide, aren't we? We're going to wind up with a tertiary alcohol, and therefore it will have 1, 2, 3 methyl groups, and it's simply terbutanol. Well, this guy's fun. Here we're going to take our our alkynyl anion as our nucleophile. This anion is going to add to the carbonyl. It's an aldehyde, so we're going to make a secondary alcohol. Secondary alcohol will have the alkene on this side and the alkyne on the other side. Once again, this is the bond we just made. And finally, here we have a vinyl lithium attached directly to our double bond here. This will be our nucleophilic carbon. It's an aldehyde, so we're going to make a secondary alcohol. Methyl group on one side, this cyclohexene on the other. And it should look like that. Once again, this is the bond that we just made. All right, so this is how we know to make alcohols, right? From way back with alkene reactions, we can hydrate them, do Markovnikov or anti-Markovnikov. We can add hydride, lithium aluminum hydride, to carbonyl. We can do Grignard reaction, or we can do alkyl or vinyl aryl lithium additions. Those are the ways we now know to make alcohols. Once we have an alcohol, what do we do with it? Hence, we have reactions of alcohols now. We can convert an alcohol into an alkyl halide. This particular reaction we use HCl gas and ether. This, basically, we're going to protonate our leaving group here. Chloride is going to be our nucleophile, and we can form our alkyl halide. This is going to form a carbocation intermediate. And just like we learned way back with alkenes, that means we can have rearrangement, and we will form the most stable carbocation, which means Markovnikov regiochemistry. This is not a great way to do this, to be honest. There are better ways to make alkyl halides from alcohols, although depending upon what alcohol you're dealing with, how stable the carbocation would be, this can work. A nicer way is to use PBr3, phosphorus tribromide. Phosphorus tribromide reacts nicely with alcohols to convert them into the alkyl bromide. This mechanism of this reaction involves, first, the alcohol as a nucleophile attacking the PBr3 to form a phosphate ester. Okay? We do that and Br minus. Our second step, Br minus, does a simple SN2 reaction. Remember those? It comes in, it attacks, the phosphate ester leaves. When it does, we get the alkyl bromide. But because this is an SN2 process, we get inversion of configuration here. Let's look at an example. Oh, well, let's do this one instead. We can also make alkyl chlorides using another reagent. This is called thionyl chloride, SOCl2. Typically, you do this in pyridine. Pyridine is a heterocyclic amine. It's a base. Mechanism of this is fairly simple, or fairly similar. Oh, this is pyridine. Again, it's a heterocyclic. You will see in chapter 14 that this is aromatic. It also has a pi system in here with delocalized electrons. It also really, really stinks. Just like with PBr3, first step is going to be the alcohol as a nucleophile on the sulfur. We lose a halogen. Here it is. And our second step, same thing. We're going to attack SN2 style, and once again we get inversion of configuration. So, alcohol plus PBr3 gives alkyl bromide. Alcohol plus thionyl chloride gives an alkyl chloride. They both proceed with inversion of configuration. Now there's actually another way to do this reaction that is not covered in the book, but I always stick it in because it's such a neat reaction. Pyridine is a polar solvent. Okay, we have the nitrogen on the end of the ring there. Makes it a nice polar solvent. It's a base. If we do this reaction instead in a nonpolar solvent, it still works. We wind up with the alkyl chloride. But because it is a nonpolar solvent, we can't, we do this by a totally different mechanism. Step one, same sort of thing, we're going to displace it, form the compound here. But our second step, the SN2 reaction does not occur. Instead, we get what's called an SNI reaction. That is, the chlorine that's attached to the sulfur just slides down as this slides up. Now this is essentially front side displacement. And because it's a front side displacement, this goes with retention of configuration. So the cute thing here is that you can control the stereochemistry by whether or not for conversion to an alkyl chloride, simply by changing from pyridine to a nonpolar solvent, we can keep retention of our configuration. With a nonpolar solvent, we get retention. With pyridine, we get inversion. Very nice test question. Give you a chiral compound like this. Again, we would get retention of our configuration. Any questions? This is a reaction that we're going to do on Thursday. Sort of. We're doing cyclohexanol to cyclohexene, but it is simply acid catalyzed dehydration. We can do this with strong acid. We can do it in a more civilized way using POCl3 and pyridine. With this, we have a carbocation intermediate. Again, we can get rearrangement, and it will be Markovnikov regiochemistry. All we're doing is protonating here, forming carbocation. Then we do an elimination, lose our proton to get this. Any question? An E1 elimination. And again, that's what we're doing on Thursday. The reaction with POCl3 and pyridine, much more civilized. Here we're going to, first of all, form a phosphate ester once again with our alcohol. And instead of the E1 elimination that we had in the previous slide, this is now set up to do an E2 elimination. So we can pull a hydrogen off. And because it's an E2 elimination, the same rules apply. This and this have to be anti and coplanar in order for it to work. All right, so we can do alcohols to alkyl halides. We can do alcohols to alkenes, two ways, one that's civilized and one that isn't. We can also oxidize. That is, we can go back from an alcohol to a carbonyl. Now there are two reagents really that we're going to talk about. One is pyridinium chlorochromate. We just call it PCC. The nice thing about pyridinium chlorochromate is that it's a very mild oxidant. And because it's such a mild oxidant, we can take a primary alcohol and take it to an aldehyde. Aldehydes are typically more difficult to make because they oxidize very quickly to carboxylic acids. The other way is what's called Jones reagent. Jones reagent is basically a chromate. If you've ever worked in a real lab, this is cleaning solution. Chromate and sulfuric acid, very powerful cleaning solution. It'll remove almost everything from old glassware. And all it does is oxidize the OH group to give us the carbonyl. This works nicely with secondary alcohols. If you tried to do this with a primary alcohol, the aldehyde would immediately oxidize to the carboxylic acid. So that's why PCC is so nice. PCC allows this reaction to occur, get the aldehyde nice and easily. And one other oxidation that's worth mentioning, if we take an allylic alcohol, again, the allylic position just does magic things sometimes. Allylic alcohol in the presence of MnO2. Now, MnO2 isn't even soluble in anything, but it's a powerful enough oxidant just on its surface to convert this to the aldehyde, and it stops there. But it only works with allylic alcohols. All right, so let's look at our set. Do these oxidations for these alcohols and give me products. This is Jones reagent, isn't it? We know that if we oxidize a primary alcohol, we would form an aldehyde. However, Jones reagent is so powerful it oxidizes the aldehyde immediately to the carboxylic acid. This is our friend PCC. Well, should be PCC. Extra P in there, sorry. This is a nice mild oxidizing agent. This will not oxidize an aldehyde, so this will stop at the aldehyde stage, and that's our product. Here we have Jones reagent again, but we're dealing with a secondary alcohol, so that's okay. This will simply oxidize the alcohol group into the carbonate. Let's make alkyl halides. PBr3 will simply change the hydroxyl group into an alkyl bromide. We know that this will go with inversion of configuration, but it's not a chiral center, so it doesn't matter. Here we have thionyl chloride and pyridine. Now we remember, thionyl chloride and pyridine is going to give us the alkyl chloride. So we're going to change that into a chlorine. But because we're in pyridine, we're going to do the SN2 reaction. Now, by George, I've drawn this as a chiral center, haven't I? Therefore, we must draw a product where we show inversion of configuration. In order to do inversion, all I have to do is change the orientation of any one group. Here I've just taken my methyl group and put it back as it used to be before. PBr3, again, the OH is going to go to a bromine. We are going to get S into an inversion, but it's not a chiral center. So we simply need to show it like that. Our first reagent here is PlCl3, not PBr3. We remember that this is what we use to make alkenes by civilized E2 elimination. That means we're not going to have a carbocation, and we're not going to rearrange. So we're simply going to lose the OH group, and the carbon here is going to be a double bond. By George, I've shown chirality here again, haven't I? We know that PBr3 is going to give us an alkyl bromide with inversion of configuration. So draw this and show inversion. Simple way to do it is just to put your bromine back. HCl and ether. Two things could happen here, right? The HCl is going to protonate this group, and it's going to leave. It's going to leave because it's going to form a benzyl carbocation. But that's safe. Once we set in the E1 SN1 process, once we set that in motion, there are two things that could happen. Chloride could attack, give us the alkyl chloride, or we could do elimination to get the alkene. In this reaction, the major product turns out to be elimination, but remember, we also could get attacked by chloride at the carbocation on this point. On an exam, I would not give you this, but I might ask you the two products that you could form by E1 or SN1. All right, a couple more. PCC oxidation and chromate oxidation. Remember, PCC is very mild. And because it's very mild, we can oxidize this to an aldehyde and it stays there. Chromate is not mild at all. Chromate will oxidize this to the carbonyl compound. However, this would be an aldehyde, and it will immediately oxidize again to the carboxylic acid. All right. Let's go back and remember what we were saying about Grignard reactions. And one of the limitations of a Grignard, if you have a polyfunctional compound and you have anything in there that's acidic, it'll simply react with the Grignard, right? That's bad. One strategy around that we use in organic chemistry is called a protecting group. Now we're just going to do this casually here because you're not to the point where you're doing more sophisticated synthesis. But let's just look at the concept of protecting groups. These are protecting groups for alcohols. Again, if we wanted to take a compound like this and convert the alkyl bromide here into a primary alcohol, we could not do this with a Grignard reaction because the Grignard reagent would react with the OH on this end of the ring. In a protecting group scheme, what you do is convert this into something that's unreactive. Then you can do your Grignard reaction and then convert it back to the OH group. If we tried to do a Grignard reaction here, the OH would simply react with the Grignard. Therefore, there are two protecting groups that we're going to look at just quickly. The first is trimethylsilyl chloride. If we take this compound and react it with trimethylsilyl chloride, the OH group will attack the silicon and we will form a silicate ester. This is unreactive for Grignards. So we do this and we make our intermediate compound. Now we can convert this into a Grignard, magnesium ether and formaldehyde, and we've made our compound. In order to get rid of our silate here, all in the world you have to do is dump it into acid. Now when you run a Grignard, you always dump it into acid as a second step, right? So this does two things at once. Protonates the oxyanion and removes our protecting group. Chlorotrimethylsilane, very powerful, very easy to use. Another one that's just really fun to think about is dihydropyran. Dihydropyran reacts with alcohols in the presence of acid. This is it, dihydropyran, to form ethers. Ethers do not react with Grignard reagents. In order to remove the dihydropyran, all you have to do is dump it into aqueous acid and poof, it comes right off. So the strategy in a protecting group is to have something on there that you can put on easily and then take off at, again, very easily at a second step. A couple specialty reactions that are also in the chapter. We learned how to make 1,2-diols. We know we can make 1,2-diols from alkenes with permanganate, or we can make an epoxide and ring open. Turns out that 1,2-diols are actually kind of neat because you can then split them in half using periodate. This is an iodic acid in the presence of sulfuric acid. What happens is we're just going to split this guy in the middle, and we're going to form aldehydes. Aldehydes and ketones. Mechanism, the iodic acid simply attacks. We get a magical concerted rearrangement. This falls off, and we're left with our aldehyde. Go ahead and do this in real life. This is a trans 1,2-diol. We know we can make that by converting an alkene into an epoxide and then doing a ring opening. So that's a per-acid reaction. If we react this with HiO4, we will simply split in between our two groups. Here's our intermediate ester that we form. Split between our two groups, and we form our dialdehyde, hexane dial. Now this is an interesting compound. I believe that you do this in lab in 235. I think they still do it. This is one of the reagents that you can use to make a very simple nylon. But we can talk about that later. Finally, let's look at the pinnacle rearrangement. Pinnacle is a 1,2-diol. If we took pinnacle and tried to do an acid-catalyzed dehydration, so we simply protonate this, and we're hoping to do an elimination. The carbocation that we form would be this one, right? This carbocation undergoes a methyl transfer. The carbocation is now at this center and winds up as a carbonyl. This is, again, a very specialized reaction. Only happens really with pinnacle, but you'll see it everywhere. Pinnacle rearrangement, again, methyl transfer, and we form a ketone. All right, let's just go ahead and do a couple quick reactions, mixing it all up. And then we'll do a couple simple syntheses. Our first reaction here, we're doing sodium borohydride. We know that this is a reducing agent. It's simply going to donate H- to our carbonyl carbon. Nice, gentle reaction. No other functionalities to interfere. We're simply going to make the alcohol. Our next reaction, we have a carboxylate ester, and we have methyl magnesium bromide. We know that when we react an ester with a Grignard, the alkoxy portion is lost, and we will add 2 moles of Grignard to this carbonyl. So that means our tertiary alcohol will have a phenyl group and 2 methyls. Oops, and there it is. Lithium aluminum hydride is a reducing agent. We will add H- to our ketone here, simply convert it into a secondary alcohol. Any questions on this set? One more. PCC, that's a nice mild oxidizing agent. If we had a primary alcohol, we will make an aldehyde. This is a secondary, so we're simply going to convert this into the ketone. An aldehyde plus cyclopentyl magnesium bromide. This is our incipient anion. It will add to the carbonyl. Because it is an aldehyde, it will make a secondary alcohol, and it will look like that. And finally, we remember that POCO3 with an alcohol is going to give us an alkene. This is a nice civilized way to do it. We will get an E2 elimination, so we don't have rearrangements. Doesn't matter here, but all we're going to do is convert this cyclohexanol into cyclohexene. Finally, the very last section of this chapter discusses thiols, the sulfur analog of an alcohol. If you look at your periodic table, what's directly under oxygen is sulfur. Sulfur, because it is lower in the periodic table, is a much better nucleophile than oxygen. When we name this thing, we're simply going to take the parent chain and stick thiol on. This is butane thiol, cyclohexane thiol, benzene thiol. If we have a polyfunctional group, mercapto is what is stuck on, usually in front, mercapto ethanol. Butane thiol, this is the essence of skunk. Thiols really stink. That's the one thing you need to remember. They really, really stink. In biochemistry, if you do any real lab work in biochemistry, Mercaptoethanol is used to reduce disulfide linkages in proteins. Use this in lots of ways. That means that the biochemistry lab stinks. Benzene thiol. I had a friend who was doing thesis work using benzene thiol, and you could literally smell him across this entire room, even though everything he did was in a hood. Still enough got on him, and it stays there for months. Yeah. They really are bad compounds.
You guys friends for much longer?
We kept them at that in the lab, so we can make them because this is such a good nucleophile. We can do a simple SN2 displacement and make our thiol that way. A much more elegant way is to use thiourea and make this intermediate salt. So this is thiourea. Urea just has an oxygen here. Again, sulfur is a much better nucleophile. What you do is you form the isothiourea, this stuff. And this is this is easily hydrolyzed in alkaline solution to give the thiol. There's one other thing about that means nothing to you yet, but it will when you do chapter 14. Thiols are also one of the best nucleophiles to do what's called nucleophilic aromatic substitution. This is not an SN2 reaction. The thiol adds to the ring and then leaves in the second step, but it's one of the few things that works really nicely in nucleophilic reactions. You don't know what those are yet. That's a problem with doing things out of order. What can I say? All right, this pretty much winds up this chapter. Now, if you look at your little handout, there are some problems that come afterwards. We are going to do those in a SN2 problem set, I guess in a week. When we're trying to decide when we're finally going to have this exam, okay? Remember, we're doing cyclohexene on Thursday. And that's it.
Is our final still on the 15th?
Is it when?
The finals is still on the 15th?
I think so. I haven't seen a change. So.
I missed class when you went over chapter 10.
Okay.
Those lecture recordings that you have on Blackboard.
We have Tuesday.
They're recordings of the